Welcome to Function Focus, Lesson 24 with Ms. Barrett. This week, we are going to discuss exponential functions, specifically exponential growth and decay, and also how to graph exponential functions. Okay. So today we're going to discuss exponential growth and decay. So students will be able to determine if an exponential function is a growth function or decay function. Okay. So just for some review, let's review what a domain is. So the domain of a function is the complete set of all possible x values in the function. So it's all the x values that the function includes, okay? The range is the complete set of all of the possible y values in the function. So domain is specifically x values, range is specifically y values, okay? And then the y-intercept is where the graph crosses the y-axis at the point 0y. So where y is any number. So if it crosses the y-axis at 2, then it will be 0, 2. Okay? Where x is always 0. So x is always 0 at the y-intercept. We're going to need these three terms when we discuss the graphs of exponential functions. Okay? So all exponential functions can be represented by the function a times b to the power of x. Okay, so here x is an exponent. And this is exactly how you know if you're dealing with an exponential function. When you have a variable in the exponent, when x is in the exponent, then it is an exponential function. Think about the name, exponent, exponential. Okay, so an exponential function involves the expression, okay, b to the x, okay. So we have a times b to the x, but b to the x is special, okay, where the base b is a positive real number other than 1. So it has to be positive. It cannot be a negative number. And it's a real number, meaning a number that can be represented on a number line, okay? And it cannot be 1. So you'll never see the b be 1, okay? The b value be 1. So we call it an exponential growth. Exponential growth, so meaning it's getting larger if as x approaches positive infinity. So we're talking about end behavior here. When x approaches positive infinity, f of x also approaches positive infinity. So if the end behavior is the same, positive infinity to positive infinity, then we call it exponential growth. We call it an exponential decay. And remember, decay means to like wither away. So exponential decay, when if x approaches positive infinity, f of x approaches the opposite, negative infinity. So notice, if it's a growth, they're both approaching the same direction. If it's a decay, then they're approaching opposite directions. So as x approaches positive infinity, f of x approaches negative infinity. Let's look at our first case. So look at the graph of y equals 2 to the power of x. Okay. So this is going to be, so let's wait. Let's wait and see what it's going to be. So what I'm going to do is, I'm going to plug in, so this is my function y equals 2 to the power of x. I'm going to plug in these x values. Wherever I see x, I'm going to plug in -3, -2, -1, and so on. Okay? And I'm going to get out f of x values or y values. So basically all I'm doing is saying 2 to the -3 power, 2 to the -2 power, 2 to the -1 power, 2 to the 0 power, 2 to the first power, 2 to the second power, and 2 to the third power. All I did was plug in the number, the x value, wherever I saw x. Okay, now you can do this a couple ways. You can go into your calculator, go into the y equals. You can plug in the function 2 to the power of x, 2 to the power of x. Okay, then you can go to make sure your window, so after you put that in, make sure your window, go to second window, and make sure where it says independent, it says ask. If auto is blocked out, just make sure you move to the right one and then press enter for ask. And what this does is it allows you to plug in any x values that you want to. So the computer will generate x values, but if you want to give it specific x values like these we have here, then you're going to need to make sure your window allows it. So now we're going to go to second table. And as you can see here, we put in our y1, our function y1. Now if I plug in -3, I get out 0.125. Okay. If I put 2 to the -2 power, I get 0.25. And I'm going to keep on going. Again, all I did was just plug in those x values into the function. So then I have 1, 2, 4, and 8. Which makes sense because 2 times 2 is 4 times 2 is 8. So 2 to the third power is 8. Now, if you don't want to do the method I just did, you can always just put them in your calculator like normal. Do 2 raised to the power of -3. And I got 0.125. 2 raised to the power of -2. And I got 0.25, okay? So you don't have to do it the other way. You could always just put it in your calculator. Now, when you're putting in these negative exponents, you have to put them in parentheses. You have to put them in parentheses, okay? So now that I have my x and y values, I'm going to graph this function, okay? And because they're decimals, I don't expect you to be perfect. I just expect you to have good estimates, okay? So we're going to estimate. So -3. Now notice that this x-axis is not counting by ones. So it has 0, then it has 3 notches, then 2. That means it's counting by halves. So this is 0.5, 1.5, then 2, then 2.5, 3, 3.5, 4. So it's counting as 0.5, but the y-axis is counting as ones. So be careful with that when you're graphing. So then I go graphing my points. So -3, which is here, 0.25, 0.125, which is really close to 0. Then -2, 0.25, which is a little bit farther from 0, just a smidge. Then -1, 0.5, which is 1/2. So you're just going up slowly. 0, 1, 1, which would be right here, 2, 2, 4, and 3, 8. Okay. Now, once I've applied my points, I'm going to connect them and extend it as you go. Extend the dots and put your arrows, right? Because what this means, these arrows mean that it goes continuously. It goes to the left towards the negatives, and it goes continuously towards the positive, okay? So now it's a couple things we need to identify from this graph. The domain, the range, the y-intercept, and the end behavior, okay? Because that's going to help us determine what kind of exponential function this is. So what we see here is the domain. So the domain, remember, is all the x values. We want to know all the x values. So we're looking now from left to right. So as we see here is that the graph goes on and on and on towards the left, which means it includes all the negative x values. And it also goes on and on and on towards the right. continuously, which means that it includes all the positive x values as well. So if it includes all the negative x values and all the positive x values, we call that all real numbers. It's an R with two backs. So one R, one back, two backs. So this is all positive x values and all negative x values. You don't have to write all positive x values and all negative x values if you understand that all real numbers is exactly that, okay? So now we've covered our x values. Now what about our y values? What y values are included? So if you see here, and I could have drawn this a little bit better. If you see here, these points down here where -3 is and -2 are really, really close to 0. They don't touch 0, but they're really, really close to 0. Okay, like really close. All right. So what we can say is if we're looking at our f of x or our y values, our range, which is our y values, we want to know what y values are included in this graph. Okay, and it's all these y values. So all these y values here, here, here. These are all included in this graph. Okay. So what we can say here is that it doesn't include, the graph doesn't include any of the negative y values. It also does not include 0 because although it gets really, really, really close to 0, it doesn't touch 0. So what we can say is that y, the range, the y's can be greater than 0. Okay, can't be equal to 0 because the graph never touches 0, but we can say that it's really close to 0. So 0's here on the y-axis, and it really gets really close to 0, but it doesn't touch 0. So the range is always going to be in inequality. Okay, always. So it's going to be greater than or less than. Okay, and the y-intercept is wherever the graph touches the y-axis. So the graph touches the y-axis here. Okay, at the point 0, because remember x is always 0 for the y-intercept 1. Okay, so the y-intercept is the point 0, 1. All right, now let's look at that end behavior. As x approaches positive infinity, so as x gets more to the right continuously, what's happening to f of x? F of x is going up. As you can see, the arrow is pointing up. So as we go to the right, the arrow is pointing up. So that means that f of x is also approaching positive infinity. So based off of what we learned about up here, that means it's an exponential growth. Okay. Another way we can determine that it's an exponential growth is by just looking at the function. So this is our b term. So 2 is b. So b is 2. So we have a times b to the x power. Here you don't see that a. That a is technically 1, right? The a is technically 1. So we can say it's 1 times 2 to the x power, right? Where a is 1 and b is 2. So because b equals 2, b is greater than 1. When b is greater than 1, you have an exponential growth. Okay, so we could have determined that this was the exponential growth without even looking at the graph. But the graph is a good visual to show you that as x approaches positive infinity, f of x is also approaching positive infinity. So therefore, it is an exponential growth. But if you just want to look at the function, we can see here that b is 2, which is greater than 1. Therefore, it's a growth. So when b is greater than 1, it's a growth. Now, I do want to highlight a special feature of this graph. This is something new that you guys are probably just learning. So this line right here, remember I said that the graph doesn't touch 0? It just merely approaches 0. Well, this line here, y equals 0, okay, we call that an asymptote. One of my favorite words in math, asymptote. Okay, an asymptote is a line in which the graph approaches, So the graph gets really close. It gets really close. It approaches y equals 0, but it never touches. So the graph approaches, but never touches. We call them asymptotes. You'll see that a lot if you end up going to Algebra 2, when you get to college level math, you will see asymptotes more often. Okay, so we call y equals 0, we call that an asymptote because the graph approaches that line but doesn't touch it. Okay. All right, let's do another example. So this was an exponential growth. We know because we saw that b was greater than 1. We could also see it in the graph. Now, what about the other one? So here we have the function y equals 1/2 raised to the power of x. Okay, we're going to do the same thing we did before. You can either put in your calculator or you can just do it by hand, or you can just do simple calculations. So if I have here the function 1/2 raised to the power of x, basically all I'm doing is taking 1/2 and raising it to the power of these x values so I can find my y values. 1/2 to the negative third, 1/2 to the negative raised to the power of -2, 1/2 raised to the power of -1, 1/2 to the power of 0, 1/2 to the power of 1, 1/2 to the power of 2, and 1/2 to the power of 3. Literally, all we did was put wherever we saw x, we put in these x values. Now, when you put that in your calculator, you can just do, now all fractions must also be in parentheses. So all negative numbers and all fractions. 1/2 raised to the power of -3 is 8. Okay, 1/2 raised to the power of -2 is 4. And you just keep going. So if I keep going, I get 8421, 0.50, 0.25, and then 0.125. Okay? All right? All right, so now let's graph it. Let's graph it using the points we just found. So we say, so again, it's just estimates. -3, which is right here, 8. -2, 4. -1, 2. 0, 1. 1.5, 2.25, 3, 0.125. So that's really close to 0. And then I'm going to connect my points again. And again, I'm not perfect. I don't expect you to be perfect either. Okay, so now let's see what's our domain. Let's look at our left to right. So our domain is our x value. So that's the horizontal axis. So the arrow goes to the left, on and on and on, which means that it includes all the negative values of x. And then the arrows also go on and on to the right, which means it includes all the positive values of x. So with all the positive values of x and all the negative values of x, that means the domain is all real numbers that are with 2 backs. Now the range is the y values that are included. So we're looking at the vertical axis with the y values. So we can see that the graph doesn't extend to the negative y values. So we don't even have to worry about the negative y values. The graph is only on the positive y values. So we can say, okay, well, does the graph include 0? It does not, because again, that's an asymptote. So this, again, here is an asymptote. Y equals 0. Okay, So the graph doesn't touch y equals 0. It just gets really, really, really close. This gets really, really close. So what we can say is that y doesn't include 0, but y can be anything greater than 0 since it's approaching 0. So, okay. All right. Now our y-intercept is where the graph crosses the y-axis. So the y-intercept is the point 0, 1. Crosses the y-axis at 1. So it's the point 0, 1. Now let's look at our end behavior. As x approaches positive infinity, what is f of x approaching? Okay, f of x is approaching negative infinity because it's going down. So as we go greater in the, get bigger in the x's, we're getting lower, we're getting smaller. Look, if I start here and I'm getting bigger in my x's, I'm going to the right, I'm getting smaller in my y's. So that means f of x is approaching negative infinity. Okay, so this is going to be an exponential decay. Now, how could I have known that it was an exponential decay without doing all of this work? Well, if you look here, we have y equals 1/2 raised to the power of x. Now, before I said if b is greater than 1, then you have exponential growth. Well, here, b is less than 1. b is 1/2. b equals 1/2, which is less than 1, but greater than 0, because remember, the b has to be a positive number. So since b is less than 1 but greater than 0 at 1/2, then we know it's an exponential decay. Okay, so if b is less than 1 but greater than 0, it's an exponential decay. And let's not forget that this line y equals 0 is our asymptote. Okay. All right. Now, last but not least, when I have something like y equals 2 to the negative x. Wow, so what changed here is that the exponent is negative. Okay, the exponent is negative, right? So that's what's special here. The exponent is negative. So when the exponent is negative, you have to flip. You have to flip the b number, or the b. You have to flip b. You have to flip b. So remember before I said, well, if b is positive, if b is greater than 1, so 2, then this would be an exponential growth. However, we have to flip this. We have to flip this too. So now, before it was 2 over 1, now it becomes, flip it 1 over 2 to the power of positive x. So you have to flip it in order to change the x from negative to positive. So where you had 2 to the raised to the power of negative x, you have to flip the b. So it was 2 over 1, now it's 1 over 2, and you make the x positive. Let me do it in another example, a couple of more examples. If I have 1/3 to the power of negative x, you would say, oh, that's an exponential decay. But no, since x is negative, I now have to flip it. So it was 1 over 3, now it's 3 over 1, and I have to make the x positive. Another example, if I have 4 over 5 raised to the power of negative x, I can't have that negative x, so I have to flip my fraction, 5 over 4 raised to the power of positive x. Okay, so you flip the b, make the x positive. Okay, so really what this is, this function is not actually 2 raised to the power of negative x. It's actually 1/2 raised to the power of positive x. Okay, and we know that 1/2 raised to the power of positive x is the same as what we had up here. So I'm just going to fill in these same numbers. Okay, you have to convert it to a positive x. You don't want a negative x. So this is going to be 8, 4, 2, 1.50, 0.25, and 0.125. Okay. All right. Same as before, because we had to flip the b and make the x positive. So it's going to look the same as the one we had before. And just graphing. Okay, so before we thought it would be an exponential growth, it's actually an exponential decay because we flipped the b value and made the x positive. The domain and range and asymptote will be the same as the one we did before because we had to change it. Okay, so as x approaches positive infinity, f of x approaches negative infinity. And note the line y equals 0 is the asymptote. Okay. Okay. All right, now. Oh, so this is an exponential decay. We had to change it because the x was negative. The exponent was negative. Okay. All right, now let's summarize what we've learned. So we've learned that, almost lost you guys there. We learned that x must be positive. Okay, x must be positive. If it's negative, you got to flip the b value and make the x positive. Okay, x must be positive. So if it's exponential growth, b is greater than 1. So b can be 1.25. B can be 1.01. It just has to be greater than 1. So an example of that is 2 raised to the x power. If it's an exponential decay, the b is between 1 and 0. So b has to be greater than 0 because it can't be negative, but it has to be less than 1. An example of that would be 1/3 raised to the power of x. Okay, and your y-intercept is always going to be, now what I didn't let you notice is that the y-intercept is always your a value. So your y-intercept is going to be 0a. Okay, it's wherever the graph touches the y-axis. So x is always 0, and it's your a value. So for example, if I have 1 times 2 to the x power, then my y-intercept would be 0, 1. Okay. All right, now let's try it out. Let's practice. So if I have, it says recognizing exponential growth and decay. State whether each function is a growth or decay and state the y-intercept. So first, what I always say is I want you to identify your a and your b. So a for this one is -5 because it's a times b to the power of x. B is the only one that has the exponent. So it's a is -5, b is 2 over 3. Okay. So that means that is looking at the b tells you whether it's a decay or a growth. Okay, since my x is positive and my b is 2/3, then that's less than 1. So this is going to be a decay. Okay, and my y-intercept is always my a value, so it's going to be the point 0, -5. And I'm done. Let's look at letter B. My A value is 8, and my B value is 3/2. Now, don't assume because it's a fraction that it's going to be a decay, because 3 divided by 2 is 1.5, which is bigger than 1. Therefore, this is still a growth. And my y-intercept is going to be my A value, which is going to be the 0.08. So don't just assume because you have a fraction that it's going to be a decay. Put in your calculator and see if it's bigger than 1 if you need to. Letter C, my A value is 10. Oh, and what I have here is a negative exponent, so I must flip that. So instead of it being 3/1, my B value is actually 1/3. Okay, I have to fix that. So that would be that would be 10 times 1/3 to the positive x value. Okay, you have to change it. So now my A is 10, my B is 1/3. So since it's a fraction that's less than 1, then this is going to be a decay instead of a growth. And then my y-intercept is going to be 0, 10. Again, I had to change it because I had to flip it, the B value, because my exponent was negative. This is the same here. Okay, my A value doesn't change. It's 1/3. But this does change. Now my B value, instead of it being 2/5, it's now 5/2. Okay, this became 1/3 times 5/2 raised to the positive x power. So since I have 5/2, which is 2.5, that's going to be a growth because it's greater than 1. And then my y-intercept is going to be my A value in the 0.0, 1/3. So that's my... Okay. Next up, I have f of x equals -4 times 8/5 raised to the power of x. My A value is -4. My B value is 8/5. I didn't have to flip that one. The x is already positive. Leave it alone. Okay. Now 8/5 is like 1.6 or something like that. It's a big number. It's bigger than 1. So then this is going to be growth. And then my y-intercept is going to be 0, -4. So your B tells you whether it's a growth or decay. Your A tells you where your graph is going to touch the y-axis. Then I have -3 times 8 raised to the power of x. My A is -3. My B is 8. And that's an ugly 8. And so because 8 is B and it's greater than 1, then it's going to be a growth. And it's going, my y-intercept is going to be 0, -3. Okay. So ladies and gentlemen, your A and your B tell you a lot. You don't have to graph it to know if it's a growth or decay, but what you do need to make sure you figure out is if the exponent is negative, you have to flip the B value and then determine whether it's a growth or decay. All right, for your practice, you have, I think, 9 problems. All you have to do here is identify your A and B, making sure that your exponent, whatever it is, whether it's T or X, is positive. Okay, making a change if it isn't positive, and determine whether it's a growth or decay, and what is the y-intercept. Okay. Hope everyone has a lovely day. Bye.